Perfect. I see a lot of names on the call that I don't necessarily know. I'm assuming a lot of precast folks. So to introduce myself, I'm Vince Polimas with Walters and Wolff Glass. I work with our pre-construction department and work very closely with Walters and Wolff's precast production pre-construction department. So we'd had an idea a while back about doing a training of Curtainwall 101. I mean, really the basics of how it works, how our systems work, and gearing it a lot for precast so that you can learn more about our systems and how they work and what they do. So I know we have a lot of glass folks on the call too. A lot of this is going to be, I guess, refresher for you. So, I mean, feel free to stay on and watch, or if you've got other things to work on, be working on them as well. But we're happy to have everyone here. As we go along, if anyone has any questions, please feel free to ask as we go. If it's something that I'm going to be covering a little later, I'll let you know, or we may just, segue and do it right then. So, all right. So let's get into it. Curtain wall 101. So what is curtain wall? So from I'm going to say architectural level, what's on the screen right now is the definition of what curtain wall is. So a curtain wall is an outer covering of a building in which the outer walls are non-structural, designed only to keep the weather out and the people in. Because the curtain wall facade carries no structural load beyond its own dead load weight, it can be made of lightweight materials. The wall transfers lateral wind loads upon it to the main building structure through connections at floors or columns of the building. Okay, this is the architectural definition of curtain wall. And what I always find interesting about this definition is that this doesn't have to apply just to the curtain wall that Walters and Wolff produces. I mean, the reality is, from a very literal definition, most of the work that we supply through Walters and Wolff Precast is also curtain wall. It's any element that is being attached to the building structure, but is not actually providing support to the building. Meaning, when you hang your precast panels on a building, those panels are not designed to keep the building standing up. They are not actually providing support to the building. They are just an outside covering of the building meant to keep the weather out and people in, right? So we all are supplying curtain wall for projects in this regard. But specifically, when we're talking to architects, no one looks at precast and says that's curtain wall. Most of the time when we use the term curtain wall in practice, it is talking about glass systems. So what is curtain wall in a glass context? It's similar to the definition we just saw. It's a non-structural system used to keep the weather out and the occupants in. It spans multiple floors, and it's designed to accommodate thermal expansion, building movement, and water diversion. That is what curtain wall is. So here's a section cut from one of our shop drawings that shows it. So curtain wall for us is anytime we have our slab edge. So the slabs of the building are stopping here, and outside of that slab edge is our curtain wall. So it's running multiple floors and it's attaching back to the slab. And we will be looking at specific details. We're starting here just that high level. So curtain wall runs past our floor lines, is hanging on the outside of the building, hangs off of anchors, not providing any support back to the structure. It's not what's keeping the building standing up. And all the loads are being applied to the structure via our anchor points. So an example of a curtain wall project, this is Natural Resources in Sacramento. This is a 100% curtain wall project. So we had a structure that we had attachments to for all of our anchors, and we hung curtain wall units off the building. And that curtain wall was glazed with glass. When we talk about glazing something, that's whatever material we're installing into the curtain wall. Most of this project was glazed with glass, but some of it was glazed with metal panels as well that we see here at this lower level. So what about storefront and window wall, right? So the point of this class was curtain wall 101, but in many cases, the word curtain wall gets used very generally. People will say curtain wall when really what they mean is a storefront or window wall, or vice versa. Sometimes people say storefront and what they really have is curtain wall. So what are these two things? So let's start with storefront. What is storefront? Storefront, of where that originates from, is literally this, storefronts, right? It is the window openings of stores. Okay, that's where the term originates from. Now, I'm going to ask some questions as we go because I do like to be a little interactive. Like if you could think about most of the time when you walk into any store, like a strip mall like this, and they've got the glass right there, what are some of the differences between an opening like this and a curtain wall that we have that's spanning multiple floors of a large building? What's some of the differences? Like what would be a major difference? Like what's our floor to floor height on most commercial buildings?
15 feet.
A lot of them are going to 15 feet now, right? They were 13 and a half for a long time, and now they're going to 15. Based on this picture that we're seeing, how tall do you think that opening is?
9 feet. 10 feet.
Probably between 9 and 10 feet. I don't know exactly which one it is, but it's one of the two. This is really one of the theoretical differences between storefront and curtain wall, right? As the architects are using it. There are companies that sell systems designed for storefronts. So here's an example from Arcadia, which is one of the off-the-shelf suppliers of glazing systems. This is their storefront system. Notice the depth of the system. It's less than 5 inches deep, okay? Compared to when we look at details for our curtain wall system, we are 7.5 inches deep minimum, sometimes going up to 9 inches, 10 inches. Why? Why do we have the difference? It comes down to the loading. When I have curtain wall, let's go back up here. These were 14.5-foot floors. When I have a curtain wall unit that's spanning 14.5 feet, it has to be able to resist the wind load and not deflect. The mullions cannot over deflect. My deflection is limited. Generally, it's limited to L over 175. So the length of my mullion divided by 175, that's how much my deflection is limited to. If I'm over deflecting, the way that I get my extrusion to work is to either add reinforcing to it or make it bigger. Because the bigger the mullion, the more it's going to resist that deflection. It intrinsically has higher structural values. For storefronts, when you're only spanning 9 feet, that need to be as deep and bulky doesn't exist. So you can do a storefront like this with a very small system. You can do it where it's only 4.5 inches deep, sometimes even less than that, because it's not spanning as big of a distance. Now, window wall. Okay, what is window wall? So this is an example we have of window wall. This isn't a project that Walters and Wolff did. This is an apartment building down in Los Angeles. So notice the difference between this and what we saw in curtain wall. Curtain wall was hanging outside the building, covering everything, right? You did not see slab edges. There were no exposed slabs, covered outside the building. Window wall goes between the floors, right? So if you look at this photo, you can see every floor line. And the glazing systems are actually inset and they're running between the floors, floor to floor, okay? Now there's a big misnomer in the industry that window wall is cheaper than curtain wall, okay? And the reality is that for us, for Walters and Wolff, That's not the case. But why do you think that there's this idea that window wall is cheaper than curtain wall? I'll give you a hint. Like, where do we see window wall used a lot? What kind of project did I say this was that we're looking at?
Residential.
It's residential. It's residential. Residential buildings do not have 13.5-foot floor to floors. They don't have 14 or 15-foot floor and floors. Residential buildings are generally designed to 9 foot 10 inches. That's the height that they do. So just as when we looked at that storefront, it only had to span 9 feet, so it could be 4.5 inches deep. Window wall, when being used in a residential application, can be much less as well. So from Arcadia's catalog as well, this is their window wall. Looks very similar to the storefront we saw, but it's deeper. Okay, now it's like 6 1/4 overall depth instead of being 4.5. Still a lot less than our systems, but this system that we're looking at here could be used in a residential application and work fine. And the smaller the profiles you have, the smaller the extrusions you're using, the lower your cost is going to be, because inherently you're using less aluminum because the parts are going to weigh less. You're using less paint because you have less surface area of parts that need to be painted. So it drives the cost down. But this is why we'll get calls from general contractors and architects that say, oh, I heard that window wall is cheaper than curtain wall. Sure, in residential applications. When you are talking about commercial applications, meaning we're dealing with 13.5-foot floor to floors or greater, I can't get this window wall system to work. A 6 1/4 inch deep window wall system is probably good for up to like 10, 11 feet. It's not going to span 13.5, and it's certainly not going to span 14 or 15. So this is where when we do window wall on a commercial building, our mullions are the same size, or window wall on a commercial building, our mullions are the same size. We're going the same depth as we would if it was a curtain wall, because they're spanning very close to the same heights. Okay. So for us today at Walters and Wolf Glass does not differentiate between curtain wall, window wall, or storefront. Meaning if there is a project that truly has storefronts on the ground floor, we're using the same kit of parts that we would use on a curtain wall. If we have a job that has window wall, we're using the same kit of parts. So and why does that work? Because we're not going after projects that use just storefront. We're not doing buildings like this. Okay, we're not out doing strip malls. We're not out doing a lot of residential projects either. So internally, we don't need to have all those different parts. If we did say, hey, let's really start going after residential projects, yes, Walters and Wolf Glass would need to develop systems that were optimized for those floor to floors, that were optimized for shorter residential floors. But because the bulk of our work that we do is commercial, we don't do that. So we don't differentiate between storefront, window wall, and curtain wall. Any questions on that before I go on? Okay. So we're going to get into, I'm going to pull out of this PowerPoint in a second, and we're going to look at some details in shop drawings, because that's going to be the best way to talk about the different parts and pieces. But the shop drawings we're going to look at first here is from a project down in Southern California called Vans, which is just a very, very clean curtain wall job. So when we look at this here, the second and third floors, these are curtain wall. You can see it's running past the floor line. We have vision glass and we have spandrel glass, and we'll talk about what those are. And then the ground floor had some storefront, but again, we'll see we used all the same kit of parts for all of these. And let me go over to Vans here. Okay. So talking about the details for a curtain wall, this right here, this is what we call our stack joint. Okay, your stack joint is where curtain wall units vertically come together. So this unit here is at the second floor. The unit above it is at the third floor. Okay. These are all unitized systems, and we're going to stay focused on unitized systems because that's the majority of work that Walters and Wolf does. So going back to this picture just quickly, this is a unit. Basically, every mullion is a unit. That's what we call modules. So these were 5-foot wide units, and their height was 1 story tall. So I've got 2 units here stacked on top of each other. So the detail we're looking at, the stack joint, is occurring right here. Stack joints always happen right above the floor line. So when we're looking at this detail, I can see my floor line here. I can see roughly dotted in my anchor, which is what we call the mat clip. We'll look at it in the plan view to see it a little bit better. And then I've got the actual extrusions for the part as well. So the curtain wall, 7.5 inches deep. Okay, so like we said, our typical parts are 7.5. The way that a curtain wall works, like we talked about, what's the point of any curtain wall? To keep the weather out and keep the people in. So let's talk about keeping the weather out. How does a curtain wall work? A curtain wall is not an aquarium. It's not designed to keep all water out. It's designed to manage the water that gets into it, meaning that if water gets into the system, it has ways to control that water and make sure that water is able to weep back out of the system and not weep into the building. The primary way that it does that is this right here that's sticking up. This is at the head of the unit. So at our stack joint, the head of the one unit has this sticking up, and this is called the chicken head. The chicken head got its name from sometime, we believe, back in the 1980s, from designers at Harmon, who were literally doing sketches on napkins while drinking and said, hey, it looks like the head of a chicken. And like, we stick with names then. So in case you think that coming up with funny names is just a Walters and Wolf thing, no, it's actually an industry-wide thing. So that's where the term comes from. And you kind of can see it, like looks a little bit like a chicken's head. The chicken head is the water line, meaning this is the point that we want to make sure water does not get past. Water is going to be able to enter into this cavity here. This is just a gasket. These little rubber blades, they act as just a rain screen. They're supposed to keep most of the moisture out, but water is going to get past and into this spot. What it can't get past is the chicken head. This is the spot. The next unit comes down, engages with that chicken head, and the height of this has to be tall enough that depending upon what the water pressures on the building are, if we need to resist 12 PSS of water or 15, the height of this needs to be sufficient that it resists that amount of water buildup that could be going on here. Everything forward of the chicken head is called the wet area, and it's also pressure equalized to the exterior of the building. Everything inside of the chicken head is the dry area. Okay, so we want to make sure that no water and minimal air gets past the chicken head because this is the dry section. If water gets back here, it's got nowhere to go but into the building. So we have to make sure that everything stays out here to the front. Okay, talking about a couple of the other like terminology and parts that we look at here. This system was 4-sided structural. So notice there's no metal on the outside of the units. I just have glass. This is a 4-sided structural curtain wall. What holds that glass on? It is structural sealant. So this is Dow 983. It's a 2-part structural sealant. For any of you that did the shop tours last week, you saw them shooting this with the guns. This is a very fast-acting, fast-cure silicone that is able to adhere that glass to the frame permanently. So there's no metal, there's no mechanical fastener that is holding this glass to the frame. What's holding it is glue. Okay, we don't use the term glue, we call it structural sealant because it sounds a lot nicer, but the reality is we are gluing the glass to the frame, and that's what's permanently holding that glass in place. Silicone can only
Alex,
adhere to two
very
sides.
good. Very good. You should go to look, participate.
I think we'll just mute there. Silicone can only adhere to two sides. So it's adhered to the glass and it's adhered to the metal frame. This part here, 276, this is a gasket. It's a silicone gasket. The structural caulking is compatible with it, but it doesn't adhere to it. So we don't get three-sided adhesion. We just have the two-sided adhesion attaching to the frame and attaching to the glass. As we move inside the building, you probably have heard a lot of times we talk about SRTs. This right here is the SRT, this part SRT 4307. SRT stands for sheetrock trim. It's meant to be a trim piece that goes on the inside of the building. If this was a little higher off the ground, there might be drywall here. So this pocket is meant to receive the drywall. Because this stack joint is so close to the floor line, they're not going to put drywall in. So we just have this little closure piece that ends up closing off that space. Our goal is that when we turn over a project in Curtainwall, like it looks complete. You're not seeing holes, you're not seeing voids, everything's complete. Now, this area can look pretty nasty because we have all the anchors here, there's insulation, there's fire safing. So these are what we call the spandrel zones. Okay, the spandrel zones are the area that's running at the floor line. Sometimes spandrel zones are managed by not putting glass there at all and putting precast or GFRC that covers that spandrel zone. When it is curtain wall though, and we're running past, there's generally something that's going to be done to close it off. In this case, it's spandrel glass. So when we talk about spandrel glass, what we have is normal glass you can see through. Spandrel glass, there is paint applied to the inside of that surface, so you can't see through it. You look up at the building, you see glass from the exterior, but you can't see through it because there's factory applied paint applied to the backside of the glass. We don't apply that paint. That is literally factory applied by our glass fabricators. So we don't make glass in-house. We do our drawings, we take off all the sizes, we take off everything, and we order that from our glass suppliers, and they ship it to us ready to install. So if it was spandrel glass, the spandrel coating has already been applied to it. Any questions before I move on? Okay, so let's look at the vertical then. So this is our typical vertical that we have. So with unitized systems, we call them male and female verticals, right? The two parts engage with each other. So the W75 5262 is the male, the W75 5263 is the female. And in the field, when we set, they engage together. I drew a note in here for the water line. If you looked at this detail in conjunction with the last one we had, this right here is lining up with that inside face of the chicken head. So again, water is going to get into these areas. This out front is just a gasket. It's a rain screen. It's going to keep most of the moisture out, but we're going to get water that gets into these pockets. We just want it to get in here and drain down and flow out through the stack joint. We want to maintain, this is our air and water line. So everything here, pressure equalized to the outside. Everything here, pressure equalized to the inside. So sometimes we'll get general contractors that come to us, or TI contractors that say, hey, I need to hang some shades to the windows on the interior, some roller shades or some blinds. Where can we attach to? We can work with them to make sure they attach only to this dry area back here. We still want to work with them on where to attach though, because what you wouldn't want to do is run a fastener that pins these two parts together. Our units are designed to move, though our units move differently than precast typically moves. Most precast systems are designed to translate, meaning they're moving side to side. Curtain wall units rack, they tip and they move. So in a seismic event, these two units may engage more, they may come apart more. That's why you see this 1/4-inch joint in the back of mullions. You can always tell when you're on a floor looking at the back of window systems, when you see this reveal on the back side of any mullion, and mullion is the term for the vertical members of a curtain wall, that is your telltale sign that it's a unitized system. Okay, if this was solid, there was no reveal back here, that means it's probably a stick system. It was a one-piece mullion. But this little reveal, that's the way walking up to any building, you can look and go, oh, this was a unitized system. You can tell because that reveal is going to, as the building moves, as earthquake happens, as thermal expansion happens, this joint is going to get bigger, smaller, just constantly allows these units to move, to rack, to do everything. But this is our water line. We don't want anything to get past that point. So here's our verticals again. It's our same vertical, but we're doing a different cut here. This is our anchor that we talked about. So this is our mat clip. Mat clip stands for multi-adjustable clip. And if in case you're like, but you said it's a mat clip, yes, it's redundant. It's a multi-adjustable clip, but I didn't do the naming. The way this works, the mat clip is an extrusion that's mounted to the deck edge. This bolt runs through the mat clip. So this is a big 9-inch bolt that runs through. We have slots here so we can move that bolt forward or backward, depending if the slab edge is too far in or too far out. And it's also slotted up and down to allow us to move this up and down. We have serrated washers to lock it in place so that we can adjust up and down as well. The units then come with a hook lug that get hung onto that bar. If we go back to this detail here, it's a little hard to see with the insulation, but this W75 5705, this dotted line right here, you follow my hand as I go around, this is a hook. So this is what hooks over that big fastener. That big bolt is like a monkey bar, okay? It's a monkey bar and the unit literally hangs down onto that bar. That's how the curtain wall hangs from the building. So you've got your mat clip, you've got your bolt running through, and you're hanging off of that bolt. The unit above does not have a mat clip, but it engages with the unit below. So that's why we have an anchorage point at every floor line. Your units are hanging down and they're engaging with the unit below it, engaging with that chicken head. So not only is that chicken head providing your air and water resistance, this chicken head is also structurally designed to withstand the loads being applied to this unit up top. It has to be designed to withstand all the wind loads and any other loads being applied from this unit above, because it's literally supporting that unit. But notice again, this big gap around in a curtain wall, I need to allow for movement. So this unit can literally slide up and down on this chicken head. I've got a gasket here and I have a little round tube here that's meant to allow that unit to move up and down, either moving up and down daily as thermal expansion causes the units to expand and contract, or during live load as floors drop and go up as there's movement and people on the floors, or during seismic events as the units are racking, it's able to slide up and down on that chicken head. Going back to this page again, not only can we see our anchorage detail, we can also see a sunshade bracket. Okay, so curtain walls oftentimes get some element that's hung off of those. And the way that we do that is with sunshade brackets attached to the mullions. So if you follow this line here, I've got this thick aluminum, 5/16 thick aluminum bar, but it's an extrusion that's coming off of the curtain wall. You can track how it runs past this gasket. We notch around the gaskets to allow it to run in. It engages into my mullion here and gets fastened in. And at that point, what can be hung on this bracket? Just about anything. I mean, we have to calc it out and make sure it works, but we can hang a lot of things on it. As an example, on this project, we didn't even provide what was hanging. It was a whole scrim wall that was going on there with perforated panels. We provided the sunshade bracket. They came out and bolted their wall that was going to hang off of it onto there. So we have to work engineering wise to make sure that not only this bracket can take the loads, but since those loads are coming back and getting applied to our mullion, that our mullions can take those loads, that our anchors can take those loads, that everything is able to be supported as we're hanging elements off of the building.
Quick question, Vince.
Yeah.
Sorry. When you have like fins and stuff hanging off, are they always field installed, or is there ever times when you guys are installing those in the shop before?
Yeah, super good question. So for us, our standard is 6 inches, especially vertically, meaning if I have elements that are going to come off of my unit and they are 6 inches or less, we're going to try to install those in the shop if at all possible. Sometimes even smaller than that, we can't. It depends what the detailing is, if there's splices that need to go. But if I have a relatively short element that's coming off my unit, I can go ahead and install it in the shop. Above that, above 6 inches, we don't like to do shop installed. And can anyone think of why we wouldn't want to put on in the shop some element that was coming off, a foot or 18 inches? Why wouldn't we want to do that in the shop?
Trucking.
Trucking and packaging, right? If I have elements hanging off my curtain wall that stick out a foot, now as I palletize those to ship out to the job site, I can't get as many units on there. I want to keep my pallets to be less than 5 feet tall because I need the crews in the field to be able to get up there and reach everything. A 6 foot tall, it's like they can't get up there. So I want to keep them under 5 feet tall. But if I have units, my mullion itself is 7.5 inches deep. If I apply another 1 foot sunshade onto it as well, now I'm getting to be with the foam between it. I can only get like 2 units on there, maybe 3 units. And we really want to get at least 5 so that not only do we have fewer pallets that go out there, but we can cut down on the number of trucks as well. So anything beyond 6 inches we'll do in the field. Now, sometimes on a tall building, the GC goes, well, can you apply those elements on the units on the floor? Meaning as we're going to set the curtain wall units, we go ahead and attach whatever it is, the sunshade, whatever is going to go on there, and we fly the whole unit up. We can do that. We prefer not to. Our stance is if we can, we want to install the curtain wall complete, and then any of those elements that hang on after the fact would go on after the fact. We would drop the building and install sunshades. We drop the building and put on any extended covers. We would do it all after. The reason being is quality. When you install a sunshade on a unit before you've hung that unit up, there's a really good chance that if there's a sunshade right next to it, they're not going to be perfectly aligned. From just the construction tolerances that we have, the construction tolerances in the shop to build the units, the chance that those 2 elements are going to be perfectly aligned is very, very small. Okay. So when we install the curtain wall complete, and then we go hang those elements, our field crews have some adjustability at that point. They can adjust how that sunshade is attaching to the bracket to make sure that everything is aligned properly. Does that take more time? Yes. Does it mean having to do swing stages or boom lifts to get to where we need to install those elements? Yes, but it does result in a quality installation as compared to installing them either before the unit were hung or in the shop. All right. This same project, we looked at the curtain wall details. I just wanted to briefly look at it. Also had what we'll call storefront, right? 10 foot tall. Okay, so instead of the floor to floor heights, their openings at the ground floor were only 10 foot tall. In theory, we could use a smaller system here, but again, we don't. We use the same 7.5 inch system everywhere. And one of the driving reasons why we do that is, and for any of you that did the shop tours last week, if you were part of the pre-construction offsite, you saw how much extra metal we always have at the end of the job and just how much extra metal we didn't even order, but gets shipped to us because the extrusion process by our extruders is so imperfect. And there's always like extra metal that they push and they ship to us. So I want to keep how many different parts I have on a project as low as possible. So it wouldn't make sense to say, hey, this ground floor, I can make it to only be 4.5 inches deep. Let's do that. I would save aluminum, but I would have a lot of additional costs with the extruder of having all these extra parts. And my shop now has different parts they need to inventory and keep track of. And my drafters have now all different details that they have to draw. And my fab department has all different parts they have to manage and make sure they're doing fab drawings for. So when we can, we just want to keep our kit of parts to be the same, even though this technically could have been a smaller system. Looking at some details here for our storefront shows us a couple other things. So we saw our detail of how a curtain wall works and how we hang down on the chicken head at either the bottom of a curtain wall, or in this case, at the bottom of a storefront or window wall, we have our starter track. So a starter track is basically like the top of a unit. It's got a chicken head, it's got everything here, a unit comes down on it. The difference is it's being applied to the structure. If we're going into concrete, I'm probably bolting that starter track in with a quick bolt. I might have embeds here, like if this was a post-tension job, or if I'm sitting on a framed wall, I would just use smaller drill flex fasteners to be able to do it. So these are two details from the same project, just different locations on the building. Some places we were going into concrete, some places we were going into stud walls. The rest of this detail is the same. The other difference here, when we sit on a starter track and we're talking about either storefronts or window walls, notice my gap is much smaller here. In fact, I don't have any gap at all. If we read this note, notch vertical to sit hard on sill member. Okay, so we literally, the vertical mullions are notched to sit directly on the chicken head, as compared to when we go back to look at this page. Remember, we had this big gap to allow for movement. I had this big gap with curtain wall to allow for movement, because if you remember, this unit is hanging from the floor above and it needs to be able to move. When we're back here, when we're talking about storefront or window wall, I don't have something to hang from above. There's not a unit above. I just have a substrate that I'm going into. So in these cases, rather than hanging the units, we dead load them to the ground. We literally are dead loading this unit onto the top of the chicken head. In a seismic event, it can still move, but it's literally just going to tip off the chicken head and tip back on, like all the weight is still getting applied to this starter track. My head detail with a storefront or window wall now looks something like this, and it has what we call a mini Mac. It's basically a little clip that gets notched in. And why do I have all this space here and all this space here? For movement. Okay, so now as this unit thermally expands and contracts, it's able to, the head can literally slide up and down on top of this clip. Seismic events, it can rack in and out of this clip. This floor above live loads down, everything is able to move. So my movement here is all coming from the top of the unit. And down here, I'm dead loaded down onto that starter track. Okay. Any questions? Here's the verticals from the storefront down at the ground floor. It's the same verticals. I won't go back to the other page, but again, we're using, try to keep it interchangeable. So my mullions for my curtain wall on this job are the same mullions I'm using down at my storefront. The only difference down on this storefront was this was captured. Okay, so when we were looking at the detail from the curtain wall, going back to it, remember, no metal on the outside. It was all four-sided structural, right? I don't have any metal out there. I just was gluing, structurally caulking the glass to the frames. My storefront has metal on the outside, but notice that I still glue it, okay? This is not an industry-wide thing. This is a Walters and Wolf thing, okay? You could easily, and a lot of the off-the-shelf systems, when they're captured, what holds that glass in place is the metal on the outside of the building. For us, we do not do that. We are still structurally adhering that glass to the frame this cap here is aesthetic. Okay, it attaches back to the vertical, but it's not designed to take all the loads. What it's designed for is to allow room that these units can get installed and everything goes together. The other thing to point out here, when we have captured system as opposed to Inviso, is thermal breaks. So aluminum, which is what we build all of our systems out of, depending upon how you want to phrase it, you could say aluminum conducts heat really, really well, meaning it allows for heat transfer really, really well. An example of that would be if any of you have ever used aluminum foil at home when you're cooking, think about when you take aluminum foil and you put it on something really hot, okay? Really hot food, really hot pan. You touch that aluminum foil is hot, right? If you take aluminum foil and put it on a hot pan and touch it, it's hot. Everyone with me? What happens the second you take that aluminum foil off of that hot pan and touch it? Is that aluminum foil hot anymore?
No.
No. That's because aluminum is incredibly good at conducting heat one way or the other. When it's on something hot, bam, you get it. Like that heat flows through instantaneously. But the second you remove it from heat, bam, it goes back to the normal temperature because it does not retain it, doesn't do anything, but it transfers really well through. So a change that happened with all in the industry over the last 20 years is going to thermally broken systems. So here we're looking at the jam member. So this is up against a wall, but it shows it well. The W75-4113 is my extrusion. I can see the inside part here. Just follow my hand. This is the inside of the mullion. These two little things here that look like little dog bones, these are the thermal breaks. These are made of plastic. Okay, and it's done by our extruders. So they come to us already installed. And then on the outside of the building, I have my aluminum cap again. So from a shop standpoint, this is one big piece. That's how it gets delivered to us. These are already attached together. But from a performance standpoint, it's actually two different extrusions with this plastic spacer. Plastic does not conduct heat nearly as well as aluminum does. So if you think of a really hot summer day and the sun is pounding down on the outside of this system, this outside aluminum piece, this could easily be 130, 140, 150 degrees if it's in the sun, because it is just going to take that radiant heat and it's going to love it. And it's going to just absorb it all up and get really hot. And if I did not have these thermal breaks, that heat would transfer through the mullion inside of the building. This is, I mean, if you go up to some window systems on a hot summer day and you touch the aluminum on the inside of the building, it can be warm because it transfers through. These thermal breaks stop that transfer. This outside piece is going to get really warm. It's enjoying that hot summer day, but it can't get past this plastic, or at least it can't get this plastic through this plastic as well as it would if this was solid. And while I'm saying as well, this is a good thing. Right? This is what buildings want. Buildings don't want to have outside temperatures transfer from the outside in. So we use thermal breaks wherever possible. In the case of this one with the captured, this little like top hat right here, this is a gasket. It's made out of plastic. It's doing the same thing. So as these outside pieces heat up, these can get super hot, but they're not going to get past that plastic. And that's what keeps it isolated from going into the building. Okay. Questions on that? Okay. Let's look at a different job that has a couple different elements on it so we can just talk about some terminology. So this is that curtain wall we looked at the very beginning, the Natural Resources Project in Sacramento. Again, bigger floors. So these were 14.5-foot floors. Also 20-story tall building. So for anyone in engineering, we know that when you're applying and you're figuring out wind loads for a building, project height is a defining factor, and taller buildings have larger loads. So for a project like this, where I'm combined and it's like I have taller floor to floors and I had a much taller building, so it has bigger wind loads. When I go, let me just pull out my page. When we go and look at this system, this was a deeper system. Okay, so when we looked at Van's details a little bit ago, that was 7.5 inches. This one, 9.5 inches. The only reason it was deeper, because the loads were greater. I'd love to have done this job at 7.5 inches because it would have cost less money. We would have had a more economical price for the general contractor and the owner. But because of the fact they wanted 14.5-foot floor to floors and we had higher loads, the system had to get deeper in order to accommodate those loads and not over deflect. But notice, other than the fact that it's deeper, this still looks very much like the detail we looked at before. For us, we keep the concept the same. Still a chicken head, still my outside wet area, water can flow out, still my dry area. It's just that it's been stretched. It's just deeper to be able to accommodate the fact that we needed a deeper system for the loads. This one was captured as well on the exterior. So you can see the thermal breaks here. So any heat that's coming, heating up this part, it's going to be resisted and not transferring into the building as well. This job did not have spandrel glass. It had shadow boxes. So what's the difference between spandrel glass and shadow boxes? Well, we said spandrel glass is where they've taken the glass itself and they've painted it, right? They've applied paint to the inside face of the glass. In a shadow box application, the glass is still just vision glass. It looks just like the rest of the glass. There's an aluminum panel, in this case, a composite panel, so it's not solid aluminum, has a plastic inside to it, that is installed between my verticals and between my horizontals that creates the shadow box. Why is it called a shadow box? Where do we think that name comes from?
Because of the shadow it creates since it's inset from the glass.
That's exactly it, right? Architects will use shadow boxes because it provides depth to the system. When you're doing spandrel glass, that paint is right here on the number 4 surface, right? So as far as your eye can see is just to that paint. I mean, it looks like in the spandrel area, it's just everything's in the same plane. By using a shadow box, they can put, in this case, it was a 3-inch gap between the glass. This can be played with. Sometimes this is back here, sometimes it's closer, but it's called a shadow box because it can create shadows. Depending upon where the sun's at, it's going to hit mullions. You're going to read shadows across the face of this. You're going to read depth. So it's entirely an aesthetic decision on the part of the design team. You know, it just provides some richness and depth to the system when they use a shadow box. It also provides richness in that it costs more money. So this is one of the things that oftentimes comes up, especially in days like today, where people are very cost conscious and looking to save money. Projects that have shadow boxes pay a significant premium compared to just spandrel glass. Why? Because with a shadow box, I now have this whole extra thing that I have to either buy out or fabricate myself, the actual panel. I have these extra clips that I have to extrude and install. My shop has to install this whole piece. They have to caulk around this. There's a lot of work that goes into putting in a shadow box. Compared to spandrel glass, it's like, it's the same as any piece of glass. It just has paint on the backside. We install it. So the only upcharge with spandrel glass is the extra amount that we pay our glass fabricator to supply it with paint on it. With the shadow box, there's a lot more work, but it's an architectural aesthetic decision. If that's what they want, they can have it. But we do see this get VE'd a fair amount. Verticals on this job, again, same thing as we looked at before, but 9.5 inches deep instead of the 7.5. Still uses our same matte clip assembly. You can see how that shadow box engages in some of that sealant work we have to do because we don't want a lot of airflow going through and between. And then just another detail here. So this job had these fins. Okay, now these fins were 9 inches. We did shop install these fins. We normally wouldn't, but this was one that they looked at and decided that this could still be done in the shop. There was a lot of talk with the design team about how these fins would work and where they'd be, because notice they were going to an intermediate vertical. Okay, they weren't going to our male female. So notice I don't have my normal sunshade bracket. So the way this worked was the fin attached to this extrusion here that attached to the side of the mullion. Looking at this detail, why might the design team not have been thrilled with this concept? Where's my thermal break and how much of a thermal break do I really have here? I don't. There's almost none. The only thing, so when this part hanging out in the sun gets really hot, it's hard attached to this aluminum, so it can transfer right through, transfers right to this member, which transfers right in here. And the only thing isolating it from my mullion then was this little shim that I had there, which is only about an 1/8 inch thick. To call something truly thermally broken has to be separated by at least 5/16 of an inch. So at best, we call this thermally improved because it's not hard against it, but it's not thermally broken. We had to do energy tests on this job to model these details to make sure they were going to work with the energy requirements of the building, because this technically is a weak spot. But it is what we had to do given the design of this building and where these were happening on the building and the loads that were getting applied there. So just some of the different things we have. We're coming up on the end of time. We've gone through everything I have. So I just want to take a few minutes here and see, like, what questions do you guys have that I can answer, or kind of figure out if there's any future trainings as it comes to glass and glazing systems that you guys would like to know about.
Well, thank you. I don't think we have anything coming to mind, but we really appreciate it.
Yeah, this is
No.
wonderful. Thank you.
That was great, Vince.
Okay, hope it was helpful.
Great.
That is
Awesome.
it. Thanks, guys. Thanks for coming. If you have any questions or think of anything else, feel free to let me know. See you
Thanks,
later.
Vince. Thanks, Vince.
Bye.
Thank you.
Thanks, guys.